Welcome to the Deep Dive, where we cut through the noise to get you well-informed, fast. Today, we're diving into a topic that's, well, it's defining our global future. The ambitious push to hit net zero carbon emissions and limit global warming. This isn't just some hopeful target, it's a firm commitment by governments and private sectors worldwide, squarely aligning with the Paris Agreement's goal of keeping warming to 1.5 degrees Celsius, or, well below 2 degrees. Our deep dive today is into a genuinely fascinating and incredibly timely piece of research. Risks of Relying on Uncertain Carbon Dioxide Removal in Climate Policy by Madeline Bindl, Morgan R. Edwards, and Raina Yoon-Kui. This study isn't just, adding to the conversation. It's taking a really sharp look at the very strategies we're considering to reach net zero, with a particular focus on carbon dioxide removal, or CDR, technologies. So our mission for this deep dive is to unpack the real-world consequences of, planning for a future with uncertain levels of CDR. What actually happens if our grand plans for these emerging technologies don't quite align with reality? This deep dive is about understanding the climate, economic, technological, and even global equity outcomes of those critical planning decisions. We'll explore how different assumptions about CDR's future feasibility could ripple across our planet and reshape our economies. So let's start with the basics. What exactly is CDR, and why is it suddenly so central to current climate strategies?
Yeah, that's the perfect place to start. At its core, carbon dioxide removal refers to technologies and practices that remove CO2 directly from the atmosphere and store it durably. Climate policymaking, particularly through these widely used integrated assessment models, or IAMs, they increasingly rely on the widespread adoption of these technologies to meet ambitious global climate goals. Without significant CDR, many of these modeled scenarios, they show that achieving targets like net zero becomes incredibly challenging, maybe even impossible within the timeframes we're talking about.
Okay, so models are leaning on this stuff heavily. What kind of technologies are we actually talking about here?
Well, when we talk about novel CDR technologies, the models most frequently represent two main types. First, there's bioenergy with carbon capture and storage, BCCS. This involves growing biomass like specific plants or trees, then using it for energy, but, and this is the key part, capturing the CO2 emissions from that process before they hit the atmosphere and storing them away permanently. The aim is for the whole cycle to be carbon negative.
Right, grow plants, they suck CO2, burn them, capture that CO2, okay. What's the other one?
The second, which is maybe getting more attention lately, is direct air carbon capture and storage, or DACCS. This uses chemical processes to literally capture CO2 directly from the ambient air around us, like giant fans pulling air through filters that grab the CO2.
Wow, like vacuuming the sky.
Kinda, yeah.
Yeah.
Once captured, that CO2 is then compressed and stored, typically in stable geological formations deep underground, locking it away so it doesn't contribute to warming.
So conceptually, they sound incredibly powerful, almost like a silver bullet for our emissions problem. But you mentioned uncertainty. Here's where it gets really interesting. Despite all this growing interest from policymakers and the private sector, you're saying these technologies are still in very early stages. How certain are we about their actual future role? What are the big ifs that could throw a wrench in our plans?
You've absolutely hit on the critical challenge. Their future role is highly uncertain, and there are significant barriers to scaling them up to a climate-relevant level. It's not just plug and play. For one, the costs are generally very high. Many of these approaches, particularly BACCS and DCCS, they typically exceed that $100 per ton of CO2 target, which is often seen as the threshold for being, economical.
So expensive to build, expensive to run.
Exactly. Then there are the resource demands. At the massive scale needed to make a real difference globally, CDR could place substantial pressure on global land and water systems. They require vast amounts of energy and material inputs. For example, BECCS, relying on growing biomass, has been highlighted for its potential to increase food and water scarcity. It competes for land, right?
Or it could be used for growing food.
Precisely. And water, too. And while the technical feasibility of storing CO2 underground geologically is pretty well proven.
We know how to do that part.
We do, technically. But the social and political hurdles for doing it at a massive scale, they're considerable. Getting public acceptance for these storage sites, finding enough suitable locations globally, dealing with local concerns, that's not trivial.
Okay, so cost, resources, public acceptance. What else?
And beyond these practical challenges, there's also a really significant concern about what's termed moral hazard.
Moral hazard. What does that mean in this context?
The worry is that relying heavily on CDR in our climate plans might inadvertently deter or slow down other crucial climate actions, like aggressively cutting emissions from fossil fuels today. The thinking goes, if we assume some future tech fix will bail us out, it might reduce the urgency to make the hard changes now. It could potentially shift the burden onto future generations or technologies that might not even pan out.
That's a lot to weigh, especially that moral hazard point. Are we essentially building this massive climate safety net that A, we can't quite afford right now, and B, might make us complacent about the fire that's already burning? So given these significant uncertainties, how did the researchers even begin to model something so unpredictable and consequential for our climate plans? How do you model an if?
That's precisely the innovative approach this study takes. They combine decision analysis with a global integrated assessment model, GCAM, in this case, to simulate what they call a two-stage decision problem. It's designed to mimic how policymakers might actually have to make decisions under this kind of deep uncertainty.
2 stages. Okay, walk us through that.
Sure. So stage 1 represents today's planning. Policymakers make a crucial assumption right now. They either plan for a future where CDR deployment is going to be high, meaning widespread, effective, relatively cheap, or they plan for low CDR, meaning it's limited, expensive, doesn't scale. Based on that initial assumption, high or low, they design a carbon price pathway. Remember, a carbon price is that cost on emissions to push for cleaner choices.
Right. The higher the price, the faster the change generally.
Exactly. And this initial carbon price is designed in their model to meet a 2 degrees C end-of-century temperature target. So that's their initial strategy, their best guess today.
Okay, so they place their bet in stage 1. Then what happens?
Then comes stage 2. Around the year 2045, they call it the learning year, sort of mid-century, the truth is revealed. Actors in the model learn the true future CDR potential. Is it actually going to be high or is it actually low?
The moment of truth.
Right. If their initial plan, their assumption from stage 1 was correct, well, they just continue as planned. Easy enough. But if they were wrong, if they planned for high and it's low, or planned for low and it's high, then they face a choice.
Okay, what are the choices if you guessed wrong?
There are 2 main paths modeled. The first path is keep the target, but adjust the policy. For instance, if they plan for high CDR but learn it's actually low, they would need to dramatically increase the carbon price after 2045 to still meet that original 2 degrees C target. They have to compensate for the missing CDR.
So slam on the policy brakes, basically.
Pretty much. Conversely, if they plan for low CDR but suddenly learn, hey, high CDR is feasible and affordable, they could actually decrease the carbon price trajectory. Mitigation becomes less costly than they thought.
Okay, that's one path. Adjust the policy to hit the target. What's the other?
This second path is keep the tax or maintain the policy. In this scenario, they stick with their initial carbon price pathway, the one they set back in stage 1, even after learning their assumption about CDR was wrong.
They just keep going.
Yeah.
Even if the conditions changed.
Yes. And the critical consequence here is, if CDR potential turns out to be lower than they planned, they'll end up missing their 2 degrees C target. They'll get higher temperature change. But, interestingly, if the CDR potential is higher than they planned for, they might accidentally achieve an even more ambitious target, like maybe hitting 1.5 degrees C instead of 2 degrees C, without even trying harder.
Wow. Okay. This really does sound like a high-stakes game of global climate chess, where every decision today has this massive ripple effect decades down the line. It totally underscores how critical these planning assumptions are. So let's get into the heart of it. What do the models predict? What are the outcomes of these different what-if scenarios, both for the climate itself and for our economies?
Absolutely. And the climate and economic outcomes, they vary substantially depending on these planning decisions and, the reality that unfolds mid-century. Let's look at some of the core findings.
Right.
Okay, consider the scenario where you plan for high CDR and you turn out to be right. High CDR is indeed feasible. In this case, global CO2 emissions don't really start declining seriously until around 2040.
A delay in action, though.
A significant delay. And this path requires a truly substantial build-out of CDR. We're talking 1.7 gigatons of CO2 removed annually by 2050, and then a massive 27 gigatons per year by 2100.
27 gigatons. How big is that?
It's enormous. For context, that's more than half of current annual global emissions from all sources. So a huge reliance on this technology.
Okay. And the temperature?
It does reach the 2 degrees C target eventually, but it comes with a higher temperature overshoot along the way. It peaks at about 0.27 degrees C above the target trajectory around 2075 before coming back down.
Doesn't sound like much. 0.27 degrees. I guess overshoots aren't great.
They're not ideal, no. Even temporary temperature peaks can accelerate things like ice melt, trigger localized extreme weather, and make it harder for ecosystems to adapt, even if we eventually get back on target. But on the upside for this scenario, it costs less in terms of the carbon price needed.
Okay, so delayed action, Big CDR alliance, overshoot risk, but lower carbon prices. What about planning for low CDR?
Right. Now, if you plan for low CDR, and you're right, meaning high CDR just doesn't materialize affordably or at scale, things look quite different, CO2 emissions decline immediately, starting now, and they're halved globally by 2050.
Much faster decarbonization.
Much faster. This path also reaches 2 degrees C, and importantly, with a lower temperature overshoot. So climatically, it's a safer path in that sense.
There's always a but, isn't there?
But the carbon price in this scenario is nearly 3 times higher in both 2050 and 2100 compared to that high CDR scenario we just discussed.
3 times higher. Ouch.
Yeah. It means a much steeper cost for emitting carbon, translating into higher energy prices, more pressure on industries to change quickly. It's a more expensive path, economically speaking, in terms of the carbon price signal required.
Okay, so those are the plan matches reality scenarios. What about the surprises? The what-ifs when the plan is wrong?
Exactly. The surprises are really revealing. Let's look at the worst-case scenario, at least in terms of policy cost. This happens if you plan for high CDR, delaying serious emission cuts.
Banking on the tech fix.
Right. But then you learn in 2045 that high CDR is actually infeasible. It's low CDR reality. And you still decide you must hit that 2 degrees C target.
So you have to make up for last time.
Dramatically.
Yeah.
This forces a huge 58% reduction in CO2 emissions after 2045, following that period of delayed action. It's like trying to stop a supertanker just before it hits an iceberg, a very abrupt, disruptive shift.
Have the result.
The end-of-century carbon price ends up being 32% higher than if you had simply planned for low CDR from the very beginning.
So planning for low CDR from the start, even if it seems more expensive initially, actually avoids that potential massive price shock later on.
Precisely. It avoids that worst-case cost scenario and the associated disruption of sudden, very stringent policy shifts mid-century. It's a hedge against being wrong about CDR optimism.
Okay, that's the costly surprise.
Oh.
Is there a happy surprise, a best case what if?
There is, sort of. This happens if you plan conservatively, you plan for low CDR, assuming the tech won't scale much.
So you start cutting emissions hard early on.
Exactly. But then, in 2045, you learn that high CDR is actually feasible and affordable, and you decide to stick to your 2 degrees C target. In this case, you can actually decrease the carbon price trajectory after 2045. Mitigation becomes easier than you expected.
Less economic pain later.
Yes. Interestingly, the model shows this causes energy-related CO2 emissions to rebound somewhat, by about 55% in the learning year, because the pressure is eased off. But here's the really exciting part. This scenario actually opens up the possibility to limit the end-of-century temperature change to 1.5 degrees C, even if you were originally only aiming for 2 degrees C.
So you overachieve on the climate goal.
Potentially, yes. It gives us an unexpected bonus in the climate fight because we did the hard work early and then got help from the technology.
That's fascinating. But there's one more what if, right? The risky one where you planned for high CDR, it fails, but you don't adjust policy. You just keep the original lower tax.
Yes, and that's a critical risk scenario. If you plan for high CDR, it turns out to be infeasible, low CDR reality, but you decide to keep the tax, increase the carbon price to compensate. Well, that leads to significantly missing the target. The study finds it results in a 0.4 degrees C temperature overshoot by 2100 compared to the 2 degrees C goal.
So almost half a degree more warming.
Which could mean far more severe and frequent climate impacts globally. More heat waves, droughts, sea level rise, all of it. It highlights the climate risk of being overly optimistic about CDR and unwilling to course correct if that optimism proves unfounded.
These scenarios also reveal stark differences in how our energy systems would need to transform and the financial costs involved. When we talk about these numbers like trillions of dollars in assets, what does that actually look like on the ground?
Exactly. The study details really profound shifts in energy transitions and costs depending on these CDR plans. For instance, planning for high CDR means there's virtually no decline in unabated fossil fuel use. Think coal and gas, without carbon capture in the electricity sector until mid-century. Then there's a phase-out, but it's not complete until around 2085.
So fossil fuels stick around much longer in that scenario?
Much longer. In contrast, planning for low CDR forces much faster change. It means an 81% decline in unabated fossil fuel use in electricity by 2050, with near total phase-out achieved by 2060.
Wow, that's a 25-year difference in phasing out fossil power.
It is. And this faster retirement under low CDR planning leads to higher cumulative stranded assets.
Stranded assets, those are things like power plants or pipelines built expecting a long life, but they get shut down early because of policy changes, right?
Exactly. Assets that become obsolete and essentially worthless much sooner than planned. The study estimates $6.7 trillion USD in cumulative stranded fossil fuel assets if you plan for low CDR, compared to $3.6 trillion USD if you plan for high CDR.
So faster action means more write-offs of old infrastructure. But what about new investments?
Right. On the flip side, that low CDR planning, the faster action plan, also drives significantly more cumulative low-carbon investments. We're talking $108 trillion USD versus $91 trillion USD for high CDR planning.
So more money flowing into renewables, energy efficiency, grids, that kind of stuff.
Correct. More investment building the clean energy system of the future.
Yeah. And what about just how much energy we use overall and where it comes from?
That differs too. High CDR scenarios actually lead to increased industrial energy demand later in the century. Why? Largely because DACCS itself is very energy intensive. By 2100, in those high CDR scenarios, DACCS alone could consume significant portions of global electricity, about 12%, and natural gas a whopping 71% just to operate the carbon removal machines.
71% of global natural gas just for DACCS. That's staggering.
It's a huge energy footprint for the removal technology itself. Low CDR planning, by contrast, leads to about 40% lower overall energy demand by 2100, partly because there's more focus on efficiency and also nearly 3 times higher electrification in the transportation sector. Less reliance on fuels, more on clean electricity.
These numbers truly paint a picture of the kind of massive financial, infrastructural, and energy system shifts we're talking about globally. It's huge. But this isn't just about abstract global averages or trillions of dollars, is it? What about the real-world impact on people in specific regions? Does it affect everyone equally?
You're absolutely right. It's definitely not equal. Planning for CDR under uncertainty has diverse and very important regional and equity implications. First, just to level set, even in the scenario where we plan for high CDR and it fully materializes, globally, about 2.8 times more CO2 is emitted than is removed between 2020 and 2100.
So even the best case for CDR doesn't mean we stop emitting? Not even close.
Not even close. It's a crucial takeaway. Even with optimistic assumptions about high CDR, global emissions still vastly outstrip removals over the century. CDR helps, but it doesn't replace the need for deep emissions cuts everywhere.
Okay, so who does the emitting and who does the removing in these scenarios?
Well, the study finds the U.S. and China have the highest cumulative CO2 emissions and the highest cumulative removals combined. Together, they account for about 34% of emissions and 39% of removals in these modeled pathways.
So the biggest emitters are also doing the most removing.
Largely, yes. But what's fascinating here is that other countries, like Brazil for instance, contribute much more heavily to removals relative to their emissions. Brazil accounts for about 9% of global removals in some scenarios, while only contributing around 2% of global emissions over the period.
So some countries might end up becoming net removers, cleaning up carbon, even if their own historical emissions are quite low.
Exactly. It points to a potential imbalance in effort and burden. Some countries might be deploying lots of land-intensive BECCS, for example, primarily for the global benefit, potentially impacting their own resources.
And this leads to the equity point, particularly for the Global South.
Yes, perhaps most critically, the study highlights that regions in the Global South, which generally have less historic responsibility for causing climate change in the first place, they face the greatest potential benefits and the greatest potential burdens from us getting the CDR planning wrong.
How so? What's the burden and what's the benefit?
Okay, let's take the burden first. If policymakers globally plan for high CDR, delay action, but then learn it's infeasible.
The costly surprise scenario we discussed.
Right. In that scenario, regions across Africa, South America, and parts of South Asia see the highest % reductions in CO2 emissions required after 2045. They are forced into the most rapid, most demanding, potentially most costly transitions because the world collectively waited too long, banking on tech that didn't deliver.
So the burden of that sudden adjustment falls disproportionately hard on them.
In percentage terms, yes. Conversely, let's look at the benefit. If policymakers plan for low CDR, act early, but then learn high CDR is feasible.
The happy surprise scenario.
Exactly. In that case, many of these same regions in the Global South benefit the most in terms of additional allowed emissions. Because the global target is met more easily, they have more room or flexibility in their own development pathways.
Wow. So the planning choices made largely in the Global North, based on assumptions about future tech, could either impose huge burdens or offer significant benefits to the Global South. It really highlights how these uncertainties can exacerbate or potentially alleviate existing global inequalities.
It really does. It puts the onus on planners to consider not just the global cost or temperature, but who bears the risks and adjustment costs of these uncertain strategies.
That's a powerful and frankly quite sobering finding. It suggests that even the best intentions in global policy could widen existing disparities if we're not super careful about these assumptions. This raises an important question then. How do factors like when we learn the truth about CDR's potential or aiming for even tougher climate targets like 1.5 degrees change this whole picture even further? Is there a point where we learn too late or aim too high given the uncertainty and the consequences just become insurmountable?
The sensitivity analysis in this study delves into exactly that. It explores how the timing of that learning year and different climate targets impact the outcomes. And yes, timing matters. There's significant value in learning early about CDR's true potential. For instance, the study shows that if policymakers learn they were wrong about CDR feasibility back in 2030 instead of 2045, and adjust course then to meet the 2 degree C target.
Learning 15 years earlier.
Right. That early learning and adjustment can reduce the total amount of fossil fuel stranded assets globally by about $1.0 trillion USD.
$1 trillion saved just by finding out sooner.
Essentially, yes. It allows for a smoother, less abrupt transition, avoiding some of those costly last-minute infrastructure write-downs. So getting better information sooner has real economic value.
Okay, what about aiming higher? The 1.5 degree C target everyone talks about?
That's where things get even more challenging, especially combined with uncertainty and delay. The analysis shows that delayed learning about low CDR potential, finding out late that the tech won't scale, coupled with more stringent limits on how much CDR is actually possible, say only 25% of the optimistic high levels, well, that combination can actually make achieving a 1.5 degree C policy infeasible in the model.
Just not possible to hit 1.5 anymore.
In those specific pessimistic but plausible conditions, yes. Even when 1.5 degrees C is found to be feasible, for example, if maybe 50% of the high CDR level is possible, and we learn that by 2030 it comes with a very steep price increase. Achieving 1.5 degrees C under those conditions nearly quadruples the end-of-century carbon price compared to a 2 degree C policy, a 267% increase. And it adds another $6.1 trillion USD in cumulative stranded assets.
Quadruple the carbon price, that's immense economic pressure.
It is. So the more ambitious the target, the higher the costs and the greater the risks associated with being wrong about CDR or learning the truth too late. The margins for error shrink considerably.
So given all this complexity, uncertainty, risk, and potential cost, what does a robust climate policy actually look like? How should policymakers navigate this?
That's the million-dollar question, or maybe trillion-dollar question. The study strongly suggests that simply relying on high CDR deployment and plans without also accelerating emissions reductions from the outset is a really risky bet. If that CDR fails to materialize, the costs skyrocket. We saw that 32% increase in carbon prices and 38% increase in stranded assets just for the 2 degrees C target. For 1.5 degrees C, those penalty numbers are even higher.
So don't just bank on the future tech fix.
Right. The recommendation is more nuanced. Policymakers should create incentives to develop and deploy promising CDR technologies. We need that innovation, but at the same time, they need to accelerate emissions reductions from the existing energy system starting now. It's a dual approach.
Hedge your bets, basically. Cut emissions hard now and push for CDR innovation.
Exactly. This dual approach increases the likelihood of ending up in that happy surprise scenario we talked about, where maybe low CDR was planned for, rapid emissions cuts are already happening, and then if high CDR becomes feasible, great. That newfound capacity can be leveraged. If high CDR adoption does become possible under this strategy, it allows policymakers to meet climate targets with potentially reduced pressure on those sectors that are really hard to decarbonize, things like heavy industry, aviation, agriculture.
And you mentioned this strategy could be more equitable.
Yes, because if you've already pushed for strong early action and that high CDR comes online, it might allow for a pathway where high-income countries, those with greater historical responsibility and capacity, can take on relatively higher emissions reductions, potentially easing the burden on developing nations. And ultimately, robust CDR innovation, if it happens, could enable us to actually ratchet up ambition in the future. Maybe we initially aim for 2 degrees C, but successful CDR makes reaching 1.5 degrees C feasible without those astronomical costs we discussed earlier. It keeps options open.
So it's about acting strongly now, fostering innovation, but not letting the hope for future innovation justify inaction today. That makes a lot of sense. So as we wrap up this deep dive, let's bring it back. What does all this mean for you listening and how we collectively think about tackling climate change? What we've unpacked today really highlights a critical tension, doesn't it? There's this immense promise of carbon dioxide removal technologies, a potential tool to help fix the problem. But there's equally significant uncertainty about whether they'll work at scale, what they'll cost, and what side effects they might have. And we've seen that our planning decisions today, based on assumptions about that uncertain future, have these profound, quantifiable impacts on our climate trajectory, on our global economy, trillions of dollars at stake, and crucially on global equity, potentially hitting the most vulnerable hardest if we get it wrong. The study also leaves us with a final, perhaps provocative thought. It underscores that the ability of our global systems, our economies, our infrastructure, our societies to adjust quickly if CDR targets aren't met might actually be quite limited in the real world, much more limited than even these complex models can fully capture. This suggests the scale of transitions required, especially if we face one of those worst-case surprise scenarios, could be even more challenging, more disruptive than the numbers alone suggest. So this raises an important question for you to consider. How much should we really bank on future technological solutions when the risks of delaying immediate systemic change are so high and potentially borne so disproportionately by those least responsible for the problem in the first place? What stands out to you when you weigh the potential costs of being wrong against the potential benefits of these emerging technologies? It's a crucial question as we navigate the path to a stable climate future.